Hello everyone, I'm Haojun, and today I'm going to talk about I4, incremental inference of inductive. Well, that's too long. Let's just call it automated verification of distributed protocols. The motivation of this project is that distributed systems are notoriously hard to get right, and the complexity of their protocols play a huge role in this difficulty. Traditionally, testing is the most common way to find and resolve bugs in our systems, and for a long time, this has been enough. However, as our system grows larger, it becomes harder to go through every possible executions. As a result, despite our best effort, our tests still miss many bugs, and these bugs can cause serious problems, such as inconsistency, loss of data, or service downtime. Fortunately, the research community has spent the last 15 years developing an alternative approach, formal verification, to build systems with strong correctness guarantees. With formal verification, we can formally prove the correctness of our system. And recently, as the verification tool become more practical, this approach has been adopted by the system community and been successfully applied to distributed systems. However, despite all its success, formal verification currently comes at a heavy price. Developers need to spend a lot of manual effort to write a proof for their system. If we have a look at existing approaches, and we will see how much manual effort required. For example, Verdi uses Quark, a no-never interactive theorem prover. And this approach requires the most manual effort in the order of person years. And Ironfleet uses Daphne, an automated theorem prover. While easier than a Quark proof, a Daphne proof is still a non-trivial task, which can take person months to complete. And recently, a more automated tool, Ivy, was proposed. Ivy operates in what is known as decidable fragment of logic to reduce manual effort, and is still sufficient to model distributed protocols. And this is still very important. As I said earlier, distributed protocols are subtle and hard to get right. Now, some of these approaches require less manual effort, and some require more. They all have something in common. In particular, they all require the human to find what is called an inductive invariant. An inductive invariant lies at the heart of all proofs, and finding it requires an intimate understanding of the behavior of the system. In the next few slides, I will introduce the concept of inductive invariant in detail. And in this project, we propose a novel way to automatically find this inductive invariant, which allows us to prove the safety property of our distributed protocols with little to no manual effort. And the key in our approach is that we can combine the power of Ivy and model checking. Here is a preview of our results. We are comparing the amount of manual effort in different approaches. For log server, a simple protocol with only 15 lines of code, Verdi takes 500 lines of code to prove this protocol. And for distributed log, Ironfleet spent a few days to find and prove its inductive invariant. Ivy can simplify this effort to less than an hour for log server and a few days for distributed log. With our tool, I4 can prove log server fully automatically. And for distributed log, I4 requires a little manual help, which takes less than 5 minutes. And then I4 can prove distributed log. Before I can introduce our approach, let me first tell how to verify distributed systems and what's the role of inductive invariant. At the high level, we want to prove our safety property holds at all states, and to show that we model our system as a state machine and consider an arbitrary execution. Starting from an initial state, our system can take a transition to another state, and another transition, and so on. In order to show the safety property holds in all these states, we use induction. We first prove that our safety property holds in the initial state, and this is the easy part. And then we need to prove that starting from a safe state and the system takes a transition, we will end up with another safe state. And this is a hard part, because the safety property is not inductive like that. Let me show you what I mean. Imagine this is the state space of a protocol. And in particular, these are the safe states. If our system is cracked, all reachable states must be safe. But there are other unreachable states. What's worse, from this state, we can have a direct transition to an unsafe state, which makes the safety property non-inductive. To prove the safety property of this protocol, we need to find a more restrictive property, an inductive invariant. Inductive invariant is first an invariant, which means it includes all reachable states. And then it's inductive, starting from a state in the inductive invariant, and we take a transition, we will end up with another state in the inductive invariant. Now, let's have a look at a real inductive invariant. Here is the safety property for distributed lock. In plain English, this means no two nodes can hold the lock at the same time. However, this is definitely an invariant of the system, but it's not inductive. However, so we need to find all these strengthening assertions to make it an inductive invariant. And this is a problem of all existing approaches. All of them relies on human intuition to identify this inductive invariant. And as our system grows larger, this effort increases rapidly. And also, the reliance on human intuition has traditionally considered as a fundamental requirement to prove this protocol's craft. However, our system shows that this may not be fundamental after all. In the rest of my talk, I will introduce a new approach to verify distributed protocols. At a high level, we want to find an inductive invariant without relying on human intuition. Our approach is based on a simple insight. Distributed protocols exhibit a lot of regularity, which means the behavior of a system doesn't fundamentally change from a small instance to a large scale. For example, in the distributed lock, the property that no two nodes can hold the lock at the same time should hold from two nodes to any number of nodes. For a more complex protocol, the quad DHT ring, the property that any naive node should have a naive successor is true regardless of the number of nodes. As far as we can tell, this insight holds for all protocols. And this regularity implies that we can use the inductive invariant from small instances to infer a generalized inductive invariant that holds for all instances. Now, how can we leverage this implication to automate the verification of distributed protocols? It turns out that finding inductive invariant for small instances is not only easier, but can be fully automated if we choose the right tool. That tool is model checking. Model checking can automatically explore the state space and find the inductive invariant. Traditionally, model checking was considered incompatible with distributed systems because it doesn't scale to any number of nodes. However, it fits out our purpose perfectly. We don't require it to check a huge protocol with potential infinite state space. We only require it to find the inductive invariant for a small finite instance. And then we can use that result to infer a generalized inductive invariant for all instances. Now you have seen the high-level approach. Let's see how our system actually works. The design of our system follows our high-level approach closely. There are two phases. First, given a protocol and its safety property in Ivy, we first instantiate a finite instance and use model checker to find the inductive invariant for this instance. And then we generalize that inductive invariant to all instances. And sometimes it's possible that the finite instance is too small to capture all behavior of this system. And in this case, we need to increase the size of the instance and try again. In the first phase, we first create a small finite instance, and then we feed it to model checker. There are three possible results. If our protocol is cracked, the model checker will provide an inductive invariant for this finite instance, which we can use in the second phase. If there's a bug in our protocol, the model checker will provide a concrete counterexample, which can guide us to debug our protocol. And finally, it's possible that the model checker just run out of memory and produce null result. In this case, we need another technique, concretization, to make the model checking problem easier. In concretization, we leverage symmetry of the protocol to reduce the search space. For example, there can be a special node first, which sends out the first message. And if we don't do anything, the model checker will enumerate all possibilities. What if the node 0 sends out the first message? What if node 1 sends out the first message? What if node 2? And here, we can manually assign first to node 1. And in this case, the model checker only need to take care of the situation where node 1 sends out the first message. And this can significantly reduce the search space. And actually, concretization is the only process in our system that requires some understanding of the protocol. Now we have an inductive invariant for the finite instance. We then pass it to the second phase to generalize it. First, we generalize it by universally quantifying every string assertions. And here are several cases. For example, if we have P n1, n2 from the finite instance, based on the regularity of distributed protocols, we guess this property may hold for any pair of nodes. Thus, we generalize it to for all n1, n2. If n1 is not equal to n2, then P n1, n2 holds. And if we concretize our protocol, the generalization requires a little more work. For example, we are still considering P n1, n2, and we concretize P n1 equals first. And in this situation, we need to specify that n1 equals first and n2 is not first implies this property. If this looks scary, that's good, because we can automatically do this for you. And now, we have a quantified version of all string assertions. We pass it with the original protocol to Ivy to check if it's correct. There are 3 possible results. First, Ivy can say, this is correct, and we're done. We have successfully proved the safety property of the protocol. Keep in mind that this correct is produced by Ivy. So no matter what happens in our system, we will never prove a wrong protocol correct. Sometimes the safety property can fail, which means that the finite instance is too small to capture all behavior of the system. And in this case, we need to increase the size of the instance and try again. And sometimes there can be some string assertions failed. And this means these assertions is too specific to this finite instance. And in this case, we just remove these assertions and try again. For more information about our algorithm, I recommend you to read our paper. In evaluation, we want to see if I4 can be used to find to prove real protocols and how much manual effort is required. It turns out that we can prove all 7 protocols in our evaluation. And we took all 6 protocols from Ivy, and we implement 2-phase commit based on its description. From all these protocols, we use the first 3 to build our algorithm, so they are well studied. And we use the rest 4 as a blind test, so we don't understand the internal of the system. And here is a summary of our results. We can fully automatically prove 4 protocols. And for the rest 3, it requires a little manual help to concretize these protocols. And all these concretizations are very simple. And it just takes less than 5 minutes. And the only thing you need to do is just to wait for I4 to complete. And this is still very fast. Even for the longest experiment, called ring, which only need 10.5 minutes. And also, if we look into the instance size, for example, the log server only requires 2 clients and 1 server. And for the longest experiment, the court, we can prove it with only 4 nodes. This strongly supports our hypothesis that the regularity of the distributed protocols appear even at a small instance. Now, here's the end of my talk. In conclusion, there are 2 points. First, the regularity of distributed protocols makes it possible to automatically infer inductive invariants of distributed protocols from small instances. And by combining the power of model checking and Ivy, I4 can verify a number of interesting protocols with little to no manual effort. Thanks for listening, and now I'm good to answer questions.
Hi, I'm John Howell from VMware Research, and can you hear me okay?
Yes.
So this is really fascinating work, and this is, obviously I've spent a lot of time manually discovering inductive invariants, but one of the questions I have, you said the only thing the human has to do is occasionally concretize models, but the human also has to derive the protocol. And did you do experiments when the protocol was incorrect? Because it seems like the hard part is when the protocol is wrong, will your inference lead you astray, or will it help you discover why your protocol is wrong and understand what's wrong about it? My intuition is that the designer does have to understand something about the inductive invariants to design a correct protocol.
If your protocol is wrong, then there will be a bug in the valid instance, and then the model checker will automatically check that instance and provide a concrete context example. So I think
did you experiment with that?
Yes, when I was implementing two-phase commit, I had several counter examples.
Thank you.
Ken Berman, Cornell. So I like this too. I'm curious about one of your examples, chord. So chord is a ring, of course, and that would obviously be a type of invariant I'd like to specify, but ringness is higher order, it's not first order. So could you comment on the limitations on the types of invariants that you can discover?
You are asking for the limitation of the invariant we can find?
Well, there's a piece of work on it showing how to take a higher order invariant and use it in first order logic, and they look at rings. Clearly you couldn't discover that, or do you discover that chord forms a ring, or is that not one of the invariants?
Actually, for chord protocol, it comes from Ivy. So Ivy already removed the high order logic from this protocol, and they have a way to bypass it. So we can, based on their result, we can automatically find lower order logic inductive invariant.
Jay Lorch, Microsoft Research. Yeah, it's great work. I had a question about the symmetry. Do you think it might be possible to automatically detect symmetries and thereby remove even the manual part of the process?
We have thought about that, and there is a backup slide to showing the symmetry of the protocol. As you can see, the red lines, the first is a special node, which sends out the first message and holds the lock initially. And in this case, human can easily find this is how to assign the instantiate concretize this protocol. But for now, I'm not sure how we can do this with machines.
Okay.
But that can be a potential future work.
Next.
I had a question. So you talked about safety. Can this be used for liveness as well?
Currently, our system doesn't support liveness proofs, but there's a prefer to somehow transfer liveness property to safety property. So if we can do that, we can automatically prove it.
Okay, got it. Thanks. All right, let's thank the speaker.